Hello, welcome to the Tim Booker channel. Wishing you an enjoyable listening experience. The book I'll be interpreting for you today is called The Brain That Changes Itself. Its subtitle is Stories of Personal Triumph from the Frontiers of Brain Science. Before delving into today's discussion, I'd like to pose a few questions to you. Do you believe individuals born blind can see the world? Can someone with only half a developed brain lead a normal life? Can your memories be artificially erased? These may sound quite futuristic, yet the answer to each is affirmative. This illustrates the miracles brought about by brain plasticity. In the book we're exploring today, rigorous scientific experiments are used to meticulously outline the reasons and characteristics of brain plasticity, as well as its significant role in learning, psychotherapy, post-injury recovery, technology, and other fields. This book can assist you in better understanding and unlocking the potential of your brain, leading to a life without limitations. Dr. Norman Doidge, the author of this book, is a renowned American psychiatrist and psychoanalyst. Also a research fellow at the Columbia University Center for Psychoanalytic Training and Research. Beyond his professional expertise, he's a best-selling author, critic, and poet, with works such as The Brain's Way of Healing, among others. I'll divide the following into two parts to discuss the book's main content for you. First, what is brain plasticity? Second, how can we harness brain plasticity? Let's start with the first part of the content. What is brain plasticity? Let's begin with a real-life case to provide you with a more intuitive understanding of brain plasticity. In 1959, a 65-year-old man in Spain suffered a stroke, rendering his right side paralyzed. Doctors believed he had no chance of recovery. However, his son refused to give up and began exercising his father based on his own ideas, inspired by infant development. He guided his father through exercises starting from crawling, gradually progressing to walking, tossing coins, washing dishes, and typing on a computer. Miraculously, after a year, the elderly man had almost fully recovered. He began working, traveling, and even climbing mountains, regaining all functions. 7 years later, he passed away due to a heart attack. Posthumously, researchers dissected his body and were astounded to find that 97% of the neurons controlling movement in his brain were dead, leading to partial paralysis. This contradicted the medical belief that functions couldn't be restored after brain damage. Yet, the elderly man managed to recover all functions through exercise, illustrating the miracle brought about by brain plasticity. There must have been changes in his brain. To comprehend how the brain changes, we need to understand its structure. The human nervous system comprises the central nervous system and the peripheral nervous system. The central nervous system includes the brain and spinal cord, acting as the body's command center, while other nerves transmitting information belong to the peripheral nervous system. This book primarily focuses on the brain within the central nervous system. The brain's main actors are nerve cells, also known as neurons, which consist of three main parts: the cell body, dendrites, and axons. The cell body stores genetic material, dendrites receive information, and axons transmit it. The information they carry is electrical signals, also known as electrical currents, which, when passed between neurons, generate neural activity. However, when these signals pass between adjacent neurons, the axon doesn't directly touch the dendrite of another neuron. There's a gap called a synapse. The synapse generates a substance called neurotransmitters, aiding the electrical signals to pass through the synapse and reach neighboring neurons, exciting or inhibiting them. Statistics show that the human brain's cortex houses 30 billion neurons capable of creating 10 quadrillion synaptic connections. It's evident that the number of synapses far surpasses the number of neurons, meaning information transmission between neurons isn't strictly one-to-one. One neuron can receive signals from multiple neurons and transmit information to several others. Neurons are interconnected, forming neural circuits or networks. This flexibility in transmission pathways among a finite number of neurons enables the brain to provide support from various directions. External factors such as learning and training induce changes in synapses, increasing or decreasing synaptic connections between neurons, thereby altering neural circuits. This is what we refer to as brain plasticity. For instance, the elderly stroke survivor we mentioned earlier lost the neurons governing movement in his brain, resulting in the disappearance of connected synapses. As a result, motor commands couldn't reach the muscles, causing partial paralysis. However, through training, some neurons in his brain, originally assigned to other tasks, partially took over the functions of the deceased neurons. This led to the formation of new synaptic connections between neurons in the motor system, enabling the transmission of movement signals and the restoration of function. In other words, neurons in the brain are versatile. They aren't restricted to fixed roles but can switch tasks. This might raise some questions because people often say that each area of the brain corresponds to a specific function or that each hemisphere of the brain has its own expertise. For example, the right brain typically handles artistic, spatial, and abstract abilities, while the left brain is more adept at logical reasoning. But are the brain's specialties innate and fixed? Not exactly. Let's consider another example, Michel, born with only half a brain. Despite this, at 29 years old, he leads a fulfilling life. His right brain manages tasks for both hemispheres, controlling his entire body. He possesses extraordinary calculation and memory abilities, swiftly recalling specific dates from years ago. However, his understanding of space and abstraction is limited. This is because different brain regions aren't limited to processing specific senses. During development, the brain selects the most capable group of neurons within a neural cluster to perform a task, a case of the capable one does more work. For instance, a part of the brain called the occipital lobe processes visual signals efficiently, earning it the label, visual center. Over time, these neural circuits tend to become relatively fixed. However, they're not entirely inflexible. Michel's half-brain situation predetermined that his brain neurons' job assignments would differ from those of an average person. With half the brain's resources missing, his existing neurons had to establish distinct synaptic connections, creating different neural circuits to explore new working paths. For example, although his right brain was intact, his proficiency in spatial and abstract thinking was limited. During development, his memory capabilities were more beneficial for survival, prompting his ability to recall events to occupy the right frontal lobe instead of the left. Consequently, his left frontal lobe, where logical connections and abstract thinking should occur, missed the chance to develop. It's akin to skiing down a mountain. The initial paths taken each time are different, but over time, a main route forms. We often follow this main route. If one day this route becomes impassable, we can still seek other smaller paths to descend. Alright, now that we've covered brain plasticity, which occurs through increasing or decreasing synaptic connections to alter neural circuits, let's discuss how this characteristic of the brain can bring changes to our lives. Next, we'll delve into the second part, how to utilize the brain's plasticity. Changes in neural circuits can manifest in three specific ways: forming new neural circuits, modifying incorrect neural circuits, and sensory redistribution. I'll explain each of these aspects separately. Firstly, the brain achieves its plasticity by forming new neural circuits. How can new neural circuits be formed? One method is by establishing fresh synaptic connections between neurons, resulting in the creation of new neural circuits. The most effective way to form new synaptic connections is through learning and training. Let's examine an experiment conducted by scientists who gathered a group of blind individuals to learn Braille. These participants attended classes from Monday to Friday and rested on weekends. Scientists used a non-invasive method to explore the subject's brain maps. Brain mapping involves dividing the brain into different areas according to function, a concept introduced by neurosurgeon Wilder Penfield in the 1930s while operating on epilepsy and brain tumor patients. He recorded and mapped brain areas related to motor sensation. He observed that body parts physically close were also adjacent in the brain map. For instance, the brain region responsible for thumb movement was next to the area controlling the index finger. After blind individuals learned Braille for some time, scientists found that the brain area dedicated to Braille learning, in the first 6 months, was significantly larger on Fridays compared to Mondays. However, by the 6th month, the map on Mondays slowly expanded until the 10th month, reaching its maximum size and stabilizing. Scientists then assessed the subjects' Monday maps after a 2-month break and discovered they were similar to those of nearly 2 months prior. Researchers believed that in the first 6 months of learning Braille, the rapid changes in brain maps from Monday to Friday were due to intensive learning, utilizing existing synaptic connections more efficiently, tightening existing neural circuit connections. After 6 months, the gradual expansion on Mondays indicated the formation of entirely new synaptic connections between neurons, resulting in the creation of new neural circuits. Though slow, these changes were long-lasting, persisting even after a 2-month cessation of learning. This resembles our studying habits. During last-minute cramming before exams, we rely on existing neural pathways, easily forgetting the information afterward. Only persistent training can establish new connections, reinforcing memory. Training also enhances neuronal efficiency. In an experiment, scientists trained monkeys to touch a rotating disc with their fingertips for 10 seconds, maintaining just the right force to allow rotation. After thousands of repetitions, researchers noted an expansion in the monkeys' brain maps corresponding to their fingertip location. Simultaneously, as the monkeys became more adept, fewer neurons were activated during the same action, indicating increased neuronal efficiency, allowing the brain to free up resources for other tasks and form new neural circuits. Apart from increasing new synaptic connections, another method involves boosting the number of neuronal cells. Traditional belief held that neurons were non-renewable. However, recent research has identified a special type of neuronal cell called neural stem cells in the hippocampus, closely linked to human memory. These neural stem cells continuously differentiate into new neurons and continually divide and replicate themselves. How can we increase the number of neural stem cells? 2 methods have been identified. Firstly, exercise. In an experiment with mice, scientists trained them to run on a wheel. After 45 days, the mice's hippocampi were measured, revealing a 15% increase in size compared to mice that didn't run on the wheel. Simultaneously, there was a 15% increase in the number of neurons. Hence, exercise promotes the growth of neural stem cells, consequently increasing the number of neuronal cells. Secondly, learning. Studies suggest that learning prolongs the lifespan of neural stem cells, subsequently boosting the number of neurons. The brain detests staying in the same environment without movement, leading to quicker atrophy. To maintain optimal brain health, constant learning of new things is crucial instead of repeating proficient tasks daily. This fosters the creation of more neural circuits. As the brain ages, having more reserve circuits becomes beneficial, emphasizing the advantage of lifelong learning. So, how can we utilize the brain's ability to form new neural circuits? For instance, in treating stroke, as we mentioned earlier, simply forcing the paralyzed limbs to move can create new neural circuits, alter brain maps, and restore limb function. It's essential to note that focused and concentrated training yields the best results. In addition to stroke therapy, forming new neural circuits can also aid in treating autism. Children with autism often display heightened sensitivity to stimuli such as sound and touch, making it challenging for them to adapt. They tend to withdraw into themselves. While autism has genetic factors, neuroscientist Merznick believes that the environment might significantly influence its development. Animals, including humans, have a critical period from birth to childhood, and they are most sensitive to specific skills or behaviors and easily affected by the environment. At birth, our brains are rudimentary sketches, which gradually refine as we encounter more external information during the critical period. During this regulation of the critical period, a substance called brain-derived neurotrophic factor, BDNF, plays a crucial role. BDNF activates a part of the brain called the basal ganglia, making it easier for neurons to form new connections, altering the shape of brain maps. In the critical period, children effortlessly absorb new knowledge. However, when the critical period ends, there's a surge in BDNF secretion that closes the switch of the basal ganglia, making the brain less prone to forming new connections. Autism arises due to the premature closure of the critical period when the brain maps haven't fully differentiated, resulting in disorganized neural circuits. Even slight stimulation can trigger widespread neural activation, surpassing sensory coherence. In a normally differentiated brain map, hearing sound A activates a few neurons, while hearing sound B activates different neurons. But in an undifferentiated brain, any sound activates the entire cortex. Scientists speculate that premature closure of the critical period might be associated with noise. Each sound heard excites one neuron in the auditory cortex, causing multiple neurons to excite together, leading to excessive BDNF production and an early closure of the critical period. Understanding the cause of autism leads to corresponding solutions. Merzenich developed a computer program that repeatedly exposes autistic individuals to monotonous tones to train their differentiated auditory cortical maps. For instance, repeated exposure to tone activates a few neurons, eliciting a specific response only to that sound. Subsequent training with another tone eventually helps the brain remap, forming new neural circuits, and alleviating autism symptoms. This therapy has shown promising results. At this point, you might wonder if it's possible to reopen the critical period in adults to facilitate easier learning. Technically, it's feasible by electrically stimulating the basal ganglia or injecting certain substances to activate it. However, such aggressive methods might cause more harm than benefit to the brain. Apart from treating stroke and autism, forming new neural circuits can help in addressing learning disabilities, dyslexia, and promoting the recovery of patients with brain injuries. The second method through which the brain achieves plasticity involves altering incorrect neural circuits. For erroneous circuits, the brain's tendency to exhaust old connections can be leveraged to weaken and dismantle the old links while establishing new ones. So, how do we achieve this? Let's take OCD, obsessive-compulsive disorder, as an example. OCD patients are constantly worried about trivial things like whether doors and windows are shut, if their hands are clean, or if items are arranged neatly, often performing repetitive actions. However, the origin of OCD lies in the brain being trapped. When we make a mistake, the brain typically undergoes three stages: first, identifying the error in the orbitofrontal cortex; second, transmitting the error feeling to the cingulate gyrus, causing anxiety and a sense of impending doom; and third, the caudate nucleus assists in shifting gears automatically after correcting the error. In OCD patients, these three regions are excessively activated, almost as if the neural circuit is stuck in the on position, particularly the caudate nucleus. This prevents automatic gear shifting, leading to incessant signaling between the orbitofrontal cortex and the caudate nucleus, creating a constant sense of error. How can this issue be resolved? First, patients need to detach themselves from their obsessive thoughts, observing the situation as a bystander without getting involved. For instance, when repeatedly locking doors, an OCD patient can imagine a camera beside them, observing the act as a bystander. Secondly, recognizing that the persistent urge to lock doors results from a problem in brain circuits. The crucial step is redirecting attention when obsessive thoughts arise, focusing on other meaningful or enjoyable activities such as listening to music, taking a walk, playing sports, or engaging in any social activity. Besides OCD, altering incorrect neural circuits can also assist individuals with psychological trauma. The book mentions a case of Mr. L, who, after his mother's death at age 2, was sent away due to family hardships. Growing up without maternal care, he became emotionally distant, refusing closeness with people. Through therapy, it was discovered that L had suppressed the idea of his mother's death, associating separation and the intense sadness together. Breaking down this psychological barrier and expressing his suppressed feelings helped L accept his mother's death and alleviate his separation anxiety. Additionally, altering incorrect neural circuits effectively treats phantom limb pain experienced by amputees. This phenomenon occurs due to the brain's construction of a missing limb. Neuroscientist Ramachandran found that disconnect between the severed limb and brain commands led to persistent pain. Using a mirror box to create an illusion of the missing limb enabled amputees to receive feedback when trying to move the phantom limb, relieving the pain over time. Beyond treating OCD, phantom limb pain, and addressing psychological trauma, altering incorrect neural circuits can be instrumental in changing negative habits like specific sexual preferences and other behaviors. The third method to achieve brain plasticity involves sensory reassignment. This process refers to the brain's ability to accept and process information from alternative sensory organs or artificial devices when a specific sensory signal to the corresponding brain region is blocked. Neuroscientist Bakwarita published an article in 1969 about a tactile device that replaced vision for congenitally blind individuals, stimulating the skin with multiple points that conveyed light and dark via vibrations. This tactile input activated the visual cortex, enabling blind individuals to perceive objects. Later, this skin-based stimulation was adapted to small electrodes on the tongue for easier portability, leading Bakwarita to suggest that the brain sees rather than the eyes. Similarly, Mesonaut's invention of an artificial cochlea works on the same principle. When worn by individuals with hearing impairment, this device converts sound signals into electronic impulses, transmitting them to the auditory cortex, allowing the perception of sound. Moreover, those lacking a sense of balance can stand upright again through tactile stimulation on the tongue. Exploiting sensory reassignment can also facilitate the creation of prosthetics that generate tactile sensations, allowing users to sense the position of the prosthetic limb. This segment elaborated on brain plasticity from 3 perspectives: forming new neural circuits, altering incorrect circuits, and sensory reassignment, showcasing applications in learning, trauma recovery, stroke treatment, and conditions like autism, OCD, and phantom limb pain. Additionally, it discussed how this neuroplasticity aids visually and auditorily impaired individuals to experience the world anew. However, brain plasticity isn't solely positive, it has negative implications. Fragmented media, like short videos, may hinder deep reading due to their rapid, attention-grabbing nature. This media form organizes the brain differently, making slower changes seem dull. Furthermore, brain plasticity can lead to addiction, not just substance or internet addiction but also inclinations like pornography and excessive exercising. Addictive substances trigger dopamine activity, strengthening the neural pathways associated with pleasure and reinforcing addictive behaviors. This addiction-induced neural change can persist even after substance cessation, leading to relapse. Childhood experiences deeply imprint neural circuits due to heightened brain plasticity during that period. Childhood trauma can affect an individual's life significantly, even impacting hippocampal volumes and long-term memory formation. Additionally, plasticity contradicts itself by solidifying certain unchangeable behaviors within the brain's territory, making it challenging to replace bad habits with good ones. Brain plasticity's discovery marks a new era, allowing a deeper exploration of the brain's potential and enabling personal transformation. Everyone has the capacity to reshape their brain and lives limitlessly with skillful application. The book Reshaping the Brain, Reshaping Lives concludes here. Until next time, thank you for your support and attention. Subscribe to the Tim Booker channel, like, and share this valuable knowledge with friends to merge wisdom with practice and achieve financial goals, creating a brighter future. Thank you, and goodbye.